Hello everyone, welcome back to another MCR3U video. And in this video we will be covering section 7.3 on creating rules to define sequences. So sometimes it might not be obvious the pattern of a certain sequence, and we may need to do some work to find the formulas for it. Here's the chapter outline once again, and you can find extra practice questions on today's topic on pages 439 to 440 in the textbook. So let's get started. We have only a couple points in our success criteria, but let's go through them. We want to be able to create a set of rules for generating sequences that are neither arithmetic or geometric. And again, like I said, these sequences may follow unpredictable patterns. So we need to set some rules to be able to define their formulas and their own patterns. We also want to learn to generate general terms and recursive formulas for sequences that are not arithmetic or geometric by finding patterns in the sequence, like I said. Let's go over some general facts that we should understand about sequences and their patterns. First, a sequence is of course an ordered list of numbers, like I said before, but it may or may not follow a predictable pattern. For example, prime numbers. Prime numbers are numbers that can only be multiplied by 1 to get the number. So 2, 3, 5, 7, 11, and no function or recursive formula has ever been discovered to generate them. This should say them. To generate them. And this is one of those sequences that is unpredictable, and there's no formula that has been found to predict further on prime numbers. Next, a sequence has a general term only if an algebraic rule using the term number, meaning where it is located in the sequence, can be found to generate each term, which we have learned before in the previous videos that you need to find a pattern involving the location of the terms, so n. Lastly, for arithmetic and geometric sequences, we can always come up with a general term as they obtain very predictable patterns, but this is not the case for every sequence. So sequences that are not arithmetic or geometric may or may not have a general term that can be generated because of their unpredictable pattern. Now we'll go over a few examples to show you how to generate these general terms and recursive formulas and the rest of the numbers in a sequence when the pattern is not so predictable. So let's do this first example, and it says determine the minimum number of moves needed to move 10 discs to another peg. And it shows us at the bottom here in the little table how many moves it takes for each disc to move. So for the first disc, it only takes 1 move. You just need to move it here. For the second disc, it takes 3 moves. Because if we want to keep the shape, but we want to move, for example, these two discs, we have to move the first one's here, then the second one here, and then the first one to the middle. So those are 3 moves, and then the next one is 7. So what pattern can we find from this table? From the number of discs to the number of moves. The number of discs acts like our location, our n value for our sequence, and this is our t of n. These values over here that keep increasing and increasing, and we need to find a pattern, right, using n to find t of n. So what patterns do we see? Well, we can actually find a recursive formula instead of a general term in this case, because if you notice, we can say that t of n will equal 2 times t of n minus 1 plus 1. Because if you notice, for example, let's take t of 2, right? So we're trying to find the term in the second position. If we plug in t of 2 minus 1, which is 1, plus 1, we plug in 1, plus 1, right? And t of 2 is going to be 2 plus 1, which is 3. So that works. Let's try t of 3 to find t of 3, which is 7. So now we're trying to find this. If we try to find t of 3, we're going to do 2 t of 2 plus 1. T of 3 is going to equal 2 times t of 2, which is 3, plus 1. 2 times 3 is going to be 6, plus 1 is going to be 7. So this recursive formula actually represents our sequence that we have down here. And even as we go on to further disks, this formula will work. And this is kind of difficult at first because you do need to think about the pattern that emerges. It won't come to you right away, but you kind of need to solve by reasoning in these types of questions. So now that we have a recursive formula, it says the minimum number of moves needed to move 10 disks to another peg. So since we found a recursive formula, all we need to do is find our next few terms until we find t of 9, which then we can use to calculate t of 10. Because remember, recursive, we need the term from before to find the next term. So let's calculate. We have t of 3. So if we calculate t of 4, it's going to be 2 times t of 3 plus 1, which is going to equal 2 times 7 plus 1, which is going to be 15. T of 4, 2 times t of 5, 2 times t of 4 plus 1 equals 2 times 15 now, right? We're subbing in t of 4 plus 1, this is going to equal 31. We'll do this all the way till 10, but I'll actually do it and I'll come back to the video because this will take quite a bit. Okay, so I'm currently at t of 9. So the 9th term, if we want to move 10 disks, right? If n equals 9, if we want to move, not 10. If you want to move 9 disks to another peg, we're going to need 511 moves. So we're just one step away from calculating t of 10. And if you want to look through what I've done, I've simply just used the recursive formula over and over again to calculate for t4, t5, t6, all the way to t9. Now to calculate for t10, we again do 2 times the previous term, which is t9, plus 1, which is going to get us 2 times 511 plus 1, which is going to be 2 times 511, it's going to be 1,022 plus 1, 1,023. So to move 10 disks from one peg to another, we're going to need 1,023 moves. But the important thing to take away from this problem is the fact that we found our recursive formula through reasoning using this table that was given to us. Okay, so moving on to the next example, it says given the sequence 5, 14, 41, 122, 365, 1,094, 3,281, and so on, determine the recursive formula for that sequence. And I've included a table here, which we'll actually use shortly, but ignore that for now. So first we want to check if the formula is either arithmetic or geometric. So to check if it's arithmetic, we see if there's a common, not ratio, but ratio for geometric, but if there's a common difference between the terms. So the difference between 14 and 5 is 9, and the difference between 41 and 14 is 27, right? So we can already see here that the differences are different, and so it's not arithmetic. Now to check if it's geometric, we take the ratios from one term to the other. So if we divide 14 by 5, we'll actually get a decimal. 14 divided by 5 is going to give us 2.8. If we do 41 divided by 14 equals 41 divided by 14, it's going to equal 2.93. 122 divided by 41 is going to equal 2.98, but we can see that it's obviously not the same factor, sorry, not the same ratio every time. So it's neither arithmetic or geometric. So we need to find a different equation to represent this sequence. We need to find a recursive formula. But if we keep going on these ratios, right, if we do now 365 over 122, we'll get 365 divided by 122 is going to give us 2.99. And lastly, let's do 1094 all over 365. We'll just do this one more time, and we'll get 2.99 again. And there's no clear pattern here, but as you can see, every single ratio is very, very close to 3. So if we, again, solve this question by reasoning, let's pretend that our recursive formula is Tn equals 3Tn minus 1. So we need to multiply the previous term by 3 to get the next, because our ratios are very, very close to 3. If we do that, and we put in a table, right, if we take Tn, and to get the next term, we multiply by 3. To get T of 2, right, we multiply T of 1 by 3, so 5 times 3 is going to get us 15. If we multiply the next one by 3, if we multiply 14 by 3, we're going to get 42. If we multiply 41 by 3, we're going to get 123. If we multiply 122 by 3, we're going to get 366, and so on. And if we finish this table, we'll actually see a very distinct pattern emerging. We can see that from Tn to 3Tn minus 1, there's just one number in between, right? So 122 is 1 away from 123, 365 is 1 away from 366, and so on until the end. So there's a very clear pattern here, and what we can decipher from this is that the recursive formula is not Tn equals 3Tn minus 1. It's actually 3Tn minus 1 minus 1, because every time we multiply by 3, we are 1 over the next term, right, of our recursive of our sequence. So if we just subtract 1, we'll be right on the term. So now, if we go over the sequence, let's do a few terms. If we find T of 2, we need 3 times T of 1 minus 1, which equals 3 times 5 minus 1, which is going to get 15 minus 1, which is 14. And that's our next term in the sequence. If we find T of 3, we'll get 3 times T of 2 minus 1, it's going to go 3 times 14, which is our next term, minus 1. And that's going to give us 42 minus 1, which is 41, which is our next term in the sequence. If we do T4, we'll just do one more. 3 times the term in the third position of the sequence, minus 1. 3 times T of 3 is 41, minus 1. 3 times 41 is going to get us 123, minus 1 is going to get us 122, which is our next term in the sequence. So we can see that we have found a successful recursive formula, and we really had no basis or where to start or where to go to find this recursive formula, but we just looked for a pattern in the numbers, and we ended up getting a recursive formula that helps us get from one term to the other. Okay, in the next example here, it says, given the sequence 3 over 4, 5 over 9, 7 over 16, 9 over 25, 11 over 36, 13 over 49, and 15 over 64, determine the general term. So, a lot of the time, and remember, general term, we need to, for the general term, we need to find an equation using the position of the term, so n. We need to find an equation that holds n in it, that uses n to calculate for the term we're looking at that position. So, a lot of the time, with fractions, what we can do is split it up between numerator and denominator. So if we do that, let's make a sequence with just the numerators. So we'll call it num numerator for numerators, and our sequence will be 3, 5, 7, 9, 11, 13, and 15. And what we can notice from the numerators is that we actually have an arithmetic sequence, because we just need to add 2 to get to the next term. 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9, and so on. And so it'll be quite easy for us to find the general term for this sequence. So our t of n is going to equal, now for the first term, we have 3. Now what can we do with n to get 3? N at this point is 1. So if we multiply 1 times 2 and add 1, we'll get 3. So if we multiply 2 times t of n minus 1, 2 times n minus 1, we'll get 3. And we could have done 3 times n, but if we continue until the next term, which is at n of 2, if we multiply 3 times 2, we'll get 6. So that will not particularly work. And again, if you don't get the general term right away and you start off with something like t of n equals 3n, which doesn't work, you test it out, and if it doesn't work, you try a different general term. There's a lot of trial and error with these unpredictable patterns because they're so unpredictable. And so this equation, this general term that we found, will work for all the numerators. And if we try some more, 5, if we plug in, if we try to get 5, which is in the second position, if we get t of 2, this is going to equal 2 times 2 minus 1. 2 times 2 is 4. Sorry, this is not minus 1, this is plus 1. Yeah, plus 1. So 2 times 2 is 4, plus 1 is going to get us 5. T of 3 is going to be 2 times 3 plus 1. 2 times 3 is 6, plus 1 is 7, and so on and so forth. So that's our general term for the numerator. Now for the denominator, right? Let's write out our sequence for denominators. 4, 9, 16, 25, 36, 49, and 64. Now, if we notice, these are all products of a number squared. So 4 is a product of 2 squared, 9 is a product of 3 squared, 16 is a product of 4 squared, 25 is a product of 5 squared, and so on until 8 squared, which gives us 64. So we're gonna be able to find a pattern in that sense. So using our n value, our first n value is obviously 1 because we're starting at the first position, but 1 squared does not give us 4. 2 squared gives us 4. So what can we do? We can add 1 to n before we square it. So if we do that, at t1, we would get 1 plus 1 squared, which is 2 squared, which is 4. At t2, we'd get 2 plus 1 squared. 2 plus 1 is 3. 3 squared is 9. t3 will give us 3 plus 1 squared. 3 plus 1 is 4. 4 squared is 16, which is our third term in our sequence, and so on and so forth. And so we have found a general term for our denominator. And I'll actually say numerator and denominator just so we can differentiate them. And now what we can simply do is put them together in the numerator and denominator to get a general term for our whole sequence, our beginning sequence up here. So our general term for our main sequence, which is going to be Tn, that's why I put an n and a d on the numerator and denominator ones, just to differentiate them. It's going to be the numerator general term and the denominator general term, which is going to be 2n plus 1 all over n plus 1 squared. that's going to be our answer. And if we plug in any number to find any of the terms, for example, let's say we want the 1, 2, 3, 4, 5th term. So if we plug in 5, we will get 2 times 5 plus 1 all over 5 plus 1 squared. 2 times 5 is going to give us 10 plus 1 is going to give us 11 all over 5 plus 1 is 6. 6 squared is 36. Right? And that's going to be our 5th term of our sequence. And we can see that this general term works, and we can move on. That is it for this lesson, everyone, and make sure to do more practice questions like these in the textbook.